Hey everybody, it's Mr. N here, and this is another review for our final. This was from the 2014 Semester 2 final, and these are the most missed questions, so let's go ahead and go over them. This video might be rather long because there are a lot of questions on here, so you might want to watch this in segments. Alright, let's take a look at this. On the first one, it says, find the limit, and on this one, we've got the limit as n goes to infinity of n squared over 2n. Now, you can take a look at this and realize that if you are taking an exponential, it's going to increase much, much more rapidly than n squared. So in this case, we're going to have a huge number on the bottom. So we will have pretty much something over an infinite number. Even though this will be infinite, this is going to be much bigger. So this limit is 0. Now, if you didn't want to think of it intuitively like that, you could L-hop it. If you L-hop the top, because if we put in infinity, we will get indeterminate, infinity over infinity. So you can L-hop this by all means, and you'll get 2n over 2n times ln 2. Well, then you're going to have to n-hop this again, and then you'll get 2 over 2n ln 2 times ln times, let's see, it's going to be 2n ln 2. Again. Okay, so in this case, you will see that the bottom does increase much more rapidly. All right, for the second one, if we put in negative infinity, we're going to get negative infinity cubed times 2 to the negative infinity. So in this case, we need to take a look at what we have here. And again, here we'll have negative infinity cubed over, now this is 2 to the negative infinity, so it ends up being 2 to the infinity. Again, this on the bottom is going to be much bigger. So you could do this with an intuitive manner, intuitive thought, and understand that that's going to be 0. If not, then you'll have to break it up and say, possibly you could say 2x over x to the negative 3 and L-hop it from there. But we're just going to go ahead and leave it at that for now. Okay, number 2. Suppose f of 1 equals 2, f prime of 1 equals 3, and f prime of 2 equals 4. Then f inverse derivative of 2 is equal to what? Well, we know what our inverse derivative formula is. Our inverse derivative formula is going to be f inverse derivative will be 1 over the derivative, and we will put the inverse of x there. So we want the derivative over the inverse. So this means we have to find what f inverse of 2 is first, before we do anything. Now, since, let's look at what we're given. Since f of 1 is 2, that means f inverse, since this is our case, we know that the inverse of 2 will be 1. So we know that answer now. So now we can say that we've got 1 over, so I'm going to continue on from this, we've got 1 over the inverse, the derivative of this, which was 1. We got this answer right here, f inverse 2, right there, to be 1. So we want the derivative of 1, which we're given that. We're given what that value is, and that value is 3. So the answer is 1/3. So the answer for this one is D. Okay, suppose that we've got this situation, and we've got y equals f of x equals 2x cubed minus 3x. If h of x is the inverse function, then h derivative inverse is equal to, now this is the same type of question here, and we have to write it as an inverse derivative. So h of x is our inverse, right? And then we've got f of 1 being, so we're going to switch this around. We're going to say x is going to be 2y cubed minus 3y. Let's put that in right now because I'm going to refer to that in a second. So we're continuing on to find this f of 1, and I'm going to go ahead and put it in this equation that I just, oops, not sure why that happened, that we just found right there. So let's go ahead and put that in there. And so this is going to be 2 times 1 cubed minus 3 times 1, and that gives me an answer of -1. And so we know, so the inverse at -1 is going to be 1. Okay, so now f prime of x ends up being 6x squared minus 3 at x equals 1 is what I'm using, so we get this value of 3. So 1 over f prime of 1 is going to be our 1/3 value. So again, the answer to this one is 1/3. All right, let's move on to the next problem. Number 4, find the absolute maximum and absolute minimum. I'm kind of pressed for space here, so I'll just try to do the best I can of this function. So let's go ahead and first find the derivative of this, because that's the process that we're going to take. We're going to get our critical points. So f prime of x is going to be 6x squared minus 6x minus 12. Okay, let's go ahead and factor this out a little bit. We're going to get x squared minus x minus 2, so we end up with 6 times x minus 2, x plus 1. Set this equal to 0. We get our critical points at x equals 2 and -1. All right, so we've got those two. Let's test these on a number line. I'm going to use the number line method for this one, so let's test these on a number line. So I've got over here -1, and then I've got over here 2. Let's test regions in between. Over here I'll end up with positives when I pick a test point. Over here I'll end up with negative, and over here I'll end up with positive. So absolute maximum, so we know that this is going to be a maximum right there. That's going to be a critical value. So we got a negative slope to a positive slope. That'll be a minimum. So we've got a max right here and a minimum at the other value. So let's test each of these. Now, I could have done this with a second derivative and find the concavity there, but I'm going to go ahead and stick to this method because we've taught this in class and this is the method that we're familiar with for now. So for part A, they've asked us to do this on -2 less than or equal to x less than or equal to 3. So I have to do this on intervals. So that means I need to test my endpoints as well. So I need to test -2. I need to test f of -2, f of 2, f of -1, and f of 3. All my critical points, including the endpoints. So f of -2 comes out to be -4. I'm putting it in the original equation to find that. F of 2 comes out to be -26. F of -1 comes out to be 7. And f of 3 comes out to be -9. So what does this give us? Well, it gives us a minimum value right here at f of 2. So this is the absolute minimum, which occurs at x equals 2, and the value is -26. Just notice something. This should be -20. Sorry. So this is the absolute minimum. It occurs at f of 2 with a minimum value of, so the value is -20, and at x equals 2. That's where it occurs. The maximum, taking a look at this, occurs right here. So the maximum is at the maximum value, the absolute maximum value is equal to 7, and that occurs at x equals -1. Okay, you can use the same process for part B, but I'm running out of space, so I'm just going to give you the answers for part B. For part B over here, the answers come out to be f of 0 equals 0, and this one yields a maximum, absolute, and then your minimum would occur at f of 3 for a value of -9. We have the same values from over here because it's the same function, so it's just different intervals, sorry. Okay, number 5. Let f be a differentiable function. F of 2 is 7, f of 4 is 2, f prime of 2 is negative 5, f prime of 4 is negative 5. The function g is differentiable on that. What is the value of g prime of 2? Again, we are looking at an inverse derivative problem. So for this one, let's take a look at what we have. So for this, we're going to write our inverse derivative. Oops, let's undo that. Let's inverse derivative of x as being 1 over f prime f inverse of x. Okay, just like what we did up above. So here we need the inverse at 2, and since f of 4 is 2, that means the inverse at 2 is 4, because that's what they give me right there. So we are looking at 1 over f prime of 4, putting it into the formula right there, which gives me negative 1/3 for this one. So the answer is B. Okay, moving on to number 6. If dy dx equals y over 2 root x, and when y equals 1, x equals 4, then a y squared equals that. So let's go ahead and go through the steps of separating the variables and solving this. So this is a separation of variables question, so let's go through this. So over here, I'm going to end up with dy over y, so I'm going to bring this y over and this dx over, equals dx over 2 root x. Okay, let's go ahead and integrate this, and I'll end up with ln, absolute value of y, equals 1/2 times 2x to the 1/2 plus c. So go ahead and go through the process of integrating that, and that's what you'll get. So we will end up with ln y equals x to the 1/2 plus c. All right, and now we're told when y equals 1, x equals 4. So let's plug this in. ln 1 equals 4 to the 1/2 plus c. I'll get 0 equals 2 plus c, so c equals negative 2. Now we know that. Now we can continue on and finish by solving this completely. So ln y equals x to the 1/2 minus 2. I put in my constant, and now we can take e to this e to each to solve for y. So we have y ends up being e. Now I'm going to rewrite this as the square root of x minus 2, like that. Let's see if this matches up anyone. If you kept it as x to the 1/2, well then you obviously, to get the right answer choice, you're going to have to change that. So for this one, we end up with e as our answer. Okay, number 7. We have the integral from 0 to 3 dx over x times the square root of x plus 1 is equivalent to what? Well, let's go ahead and try doing a substitution rule here. Let's let u equal this square root of x plus 1. So now du will be 1/2 x plus 1 to the negative 1/2 dx. So let's say u of 0. We get 1. U of 3. The reason I'm doing that is to see if I have to resubstitute or not, because my answers, take a look at my answers, they're all in u. So since they are all in u, that means I will not need to resubstitute. So I need to change the bounds by putting them in right now. So substitute the bounds as well, I should say. So now we end up with du over this 1/2 x plus 1 to the negative 1/2 is what our dx is. Now if we integrate this and put this into our integral, the integral from 0 to 3 ends up being the integral from 1 to 2, and this is where I got those values right there, from 1 to 2 of, let's make our substitution, this will be 2 square root x plus 1 over x times root x plus 1 du. Those will go away, which will give me, let's finish it over here, 2 times the integral 1 to 2 of 1 over x du, but I know what my substitution was over here, which is when I changed my let u equal the square root. So I'm going to resolve that. So this one, if I have u equals the square root of x plus 1, I have u squared minus 1 is what x is going to be. So this ends up being 2 times the integral from 1 to 2 of u squared minus 1 du. Now let's see where that, it's actually 1 over, sorry, 1 over that answer. So let's see where we end up with that. So where do we have our u, and it's going to be a for this one. I'm sorry, it's going to be b. Here's our 2, so let's use this. Here's our 2, and here's our 2. Then we have over the u squared minus 1. So the answer for this one is B. Okay, number 8, average value on its domain. Well, what is the domain? We got to find that. The domain, take a look. This is going to be a semicircle. If you look at this, and it's going to be from 8 over here, from negative 8 to 8. So the domain is from negative 8 to 8. And the average value, that means I need to say 1 over, here's our a, here's our b minus a times the integral from a to b. So this ends up being 1 over 8 minus negative 8 on the integral from 8 to 8 of the square root of 64 minus x squared. And remember, this is the area under the curve. That's what we're looking at when we integrate. So you could just take a look at this and find this area, which is the area of a semicircle. So we end up with 1/16 times 1/2 pi times 8 squared, which gives me 2 pi when all is said and done. So there's your answer. Again, the key here is notice that what does the integral mean? It's the area under the curve, but in this case I'm taking the average value of it. Okay, let's go ahead and move on to number 9. So taking a look here, it says using the substitution u equals 2x plus 1, the integral from 0 to 2 of 2x plus 1 is equivalent to. So again, this is like the previous problem. Let's go ahead and find what u of 0 is. And u of 0 is going to be 1. And u of 2, so we're looking at these bounds right here, u of 2 will end up being 5. So now we've got the integral from 1 to 5, and we're going to make our u substitution. So this will be the square root of u. And over here, since we have u equaling that, du will equal 2 dx. So du over 2 is our dx. So this becomes du over 2. And then we end up with 1/2 times the integral from 1 to 5 of the square root of u du. Again, it's like the other one. Since these bounds, everything's in u, I need to resubstitute those in there. So the answer for this will end up being C. Okay, moving on to number 10. It says, the rate at which the volume V of water in a tank with respect to time t is directly proportional to the square root of the volume. Which of the following differential equations describes that relationship? So over here, what it's saying is that the volume of the water with respect to time is directly proportional. So that means dV dt is directly proportional to the square root of V. Okay, so here we could say that dV dt equals k, some constant that we have, times our square root of V. So let's see if we have that shows up there, and that answer will be E. Okay, moving on to the next one now. For number 11, let R be the region in the first quadrant bounded by. Well, this is a big question. We got multiple parts, so let's just tackle each part at a time and then kind of go from there. So we've got that equation, and this looks like something. I will graph this up here, and we'll just refer to it up here. And I'm going to see where I'm going to have to squeeze in all this room, so I'll do some of the work up there and then some down there. Okay, so let's graph this first. So this looks like it's 2 root x and then y equals 6. So y equals 6 will be up here, and then 2 root x will be this type of curve. And these should intersect if you set them equal to each other for squared. So this should end up at 9 right here. So this ends up 3 equals the square root of x. So 9 is our x. So that's where they intersect right up there. All right, let's take a look. For part A, find the area of R. Well, there's our region R. The area, we're going to take our slices right here, top curve minus the bottom curve. So for part A, the area is going to be the integral from 0 to 9 of this 6 minus 2 root x dx. And integrating this, you'll get 6x minus 4/3 x to the 3 halves on the bounds from 0 to 9, and that comes out to be 18. Okay, for part B, it says find the volume of the solid generated when R is rotated about the x-axis. So this time for part B, we've got our solid here, and we're going to rotate this about the x-axis, so we're going in this direction. We need our slices perpendicular to that. So we're going to do that. Now, we have washers going on here. So this is going to be the big R, or the little r, minus the big R. Here, the big R minus the little r gives us this leftovers right in here that we're going to rotate about the axis. So we use washers, and we will set this up to be the volume is pi times the integral. And now this is going to go, since we're taking our slices perpendicular, dx is like this. We're going to go from 0 to 9. And this is going to be big R squared minus little r squared. And this will be pi, the integral from 0 to 9 of 6 squared minus 2 root x, that squared, dx. And this ends up being, let's see, volume will be pi, integral 0 to 9. This will be 36 minus 4x dx when we clean this up. So we'll end up with 36x when we integrate pi times 36x minus 2x squared on the bounds from 0 to 9. And when all is said and done, you'll get 162 pi. So I'll let you do that work in between to save some time. All right, for part C, now it says find the volume when it's rotated about the y-axis. So now, same situation, but we're going to take this over here, and we're going to go this way. So take your slices perpendicular. Now we need dy's. So since we need dy's, we need to know how high up we go, and we already know that it's going to go from 0 to 6. So we need these equations to be in terms of y, so we can quickly solve each of these. So y equals 2 root x ends up being 1/2 y is equal to the square root of x. So x will be 1/4 y squared. And this one is just going to remain the same, since we don't need to worry about here. We just need a disk. We don't need to actually do washers, because we're going in this direction. So we're going from 0 to 6. Only one curve to deal with. So the volume will end up being pi on the integral from 0 to 6, and this will be 1/4 y squared dy. Squared right there, sorry about that. And this ends up being pi times the integral from 0 to 6 of 1/16 y to the 4th dy, which comes out to be, when all is said and done, after you integrate to save some time and space here, 486/5 pi. So you can pause the video if you want and do those steps in between. All right, let's do part D. Let's move this down over here and work with it down here. So for part D, we've got write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the line y equals 9. So again, we've got this situation going on, and this is up at 6, here's 9, and we want to rotate this about the line y equals 9. So way up here is y equals 9, and we're going in that direction around it. So it says write but don't evaluate. So what we've got here is an outer radius and an inner radius. So the volume is pi times going to be, since I want my slices to be perpendicular to the axis of rotation, we will need dx's. So we'll go from 0 to 9 because our slices are going along the x. So from 0 to 9. Now, I need an outer radius squared minus an inner. So let's see how we're going to handle this. In this case, the outer radius is going to be this 9 minus that 2 root x equation. So the outer radius is the bigger one, so 9 minus that 2 root x. Because the line is above it, we're going to say the line minus our equation, line of rotation minus our equation since it's above it. Over here, the inner radius will be simply 9 minus 6, because our equation is y equals 6. So the volume is 0 to 9, that, and we need a dx here at the end. So cleaning all this up, we get volume equals pi times the integral from 0 to 9 of, this ends up, we'll just leave this as 9 minus 2 root x squared, and we'll leave this one, this is 3 squared, which will be 9, and we'll write this as dx right there. So we simplify that just a little bit. Okay, let's look at the next one. Moving this up so I've got a little bit more room. Part E, right, but do not evaluate an integral expression that gives the volume of the solid general when r is rotated about the line. This time it's going to be x equals negative 2. So let's just draw out what we got here. Since we got the line x equals negative 2, we've got this, x equals negative 2 is back here, so we are going in that manner around it. So again, we need an outer radius minus an inner radius. We're taking our slices perpendicular, so these will be dy's this time. So the volume is going to be from pi from 0 to 6, so we'll go from the bottom to the top here, 0 to 6. And we already solved our equations right up here. If you recall, we've got this one. So that's all we need right there. And this will end up being the outer radius, outer, squared, minus the inner, squared. So the outer radius ends up being 1/4 y squared. So that's going to be 1/4 y squared plus the 2. So it's going to be minus our line of rotation in this case, because we're coming back this way. So this will be 1/4 y squared minus our line of rotation, so that's minus negative 2. This squared minus the inner, which is just going to be 0, minus our line of rotation squared. And this will be dy in terms of y. So let's just clean this up a little bit. We've got pi 0 to 6. This ends up being 1/4 y squared plus 2 squared, and then here we can clean this up. This will be minus 4, and we've got our dy. So we write, but don't solve. All right, so part F now. Let's look at what we got here with part F. Part F says that we need the region R is the base of a solid for this cross-sectional perpendicular to the x-axis are semicircles. So let's take a look at, this is the figure that we have when we put it on the axis. Now, the perpendicular to the x-axis would be this way, and these solids are semicircles. So you've got semicircles coming out again at you, out of this, straight out at you, forming that solid. So semicircles, since we're dealing with semicircles, the area is 1/2 pi r squared. So in this case, we know the volume is the integral of the area. So the area that we're dealing with is semicircles. So this will be a sub x dx because it's going this way along the x-axis. So we're going to go from 0 to 9. So the volume is going to be the integral from 0 to 9. And this will be 1/2 pi r squared. Let's set up the area first so you understand where I got, so I can substitute the r right here. All right, so what is our r? Our r, the diameter, we know is all the way across here, and the diameter is going to be this curve 6 minus our 2 root x. This is 6, this curve is 2 root x. So that's our diameter. So our radius is 1/2 that. So taking a look at this, we've got a radius that is equal to 1/2 6 minus 2 root x, and we're going to substitute that in. So our volume is going to be the integral from 0 to 9 of 1/2 pi times 1/2 times 6 minus 2 root x, all of that squared. And then we can clean this up a little bit. Okay, so cleaning this up just a little bit, we end up with the volume from 0 to 9 of 1/2 pi. Actually, we could take that out in front in a minute here. And this part on the inside becomes 3 minus root x squared, and this will be dx's. I forgot to put the dx there. So these are dx's. Okay, if you go through, go ahead and integrate this, and again, to save time and space here, because I'm running out of it, we integrate, you're going to end up with 27 over 4 pi. And these are going to be cubic units. All right. So finally, let's get to part G over here. It's the same thing. This time the cross sections perpendicular to the y-axis are squares. So let's draw out what we have. We've got this situation. Perpendicular to the y-axis is in this direction now. So we are looking at slices that are dy's, and these coming out at you will be squares. So you'll have squares here coming out at you. So let's go ahead and see if we could set this up. Since we've got a square, the area is going to be the side squared. The side is just going to be this minus this, which is, in this case, we already solved it. It's going to be 1/4 y squared minus 0. So the side is 1/4 y squared minus 0 squared. So that's our area, and the volume is the integral of the area. So in this case, we're going to go from 0 to 6. Cleaning this up real fast, we're going to end up with 1/16 y to the 4th. So we've got 1/16 y to the 4th dy right there. And you can go ahead and integrate this, and you will get 97.2 cubic units for the volume. Again, these slices were perpendicular this way to the y-axis. Okay, let's move on to the next problem. On this problem, we've got a slope field. So since we are dealing with this slope field, it says, which of the following differential equations can be represented by that? So for this problem, there's probably the easiest way to do it is to just test out points. So these are, remember, dy dx is your slope. So what you want to do is you want to go through and pick a point. So let's pick this test point. You can pick 0, 2. And then try it in each one of these equations and see if it gives you a slope that looks like it's 0. Try all these. 1, 0. 1, 1. So any one of these, and use these as your points to try so that you end up with the slope that it looks like. So the correct answer for this one, when you do that, will end up being D. All right, for number 13, again, we're kind of moving through this a little bit fast. For number 13, find a particular solution, y equals f of x to the differential equation with this is our initial condition, and that's our differential. dy dx is 4x over to e to the 2y. So let's go ahead and separate the variables out for this one. So we're going to end up with e to the 2y dy equals 4x dx. So on this one, let's go ahead and integrate each side. When we integrate each side, we're going to end up with 1/2 e to the 2y equals 2x squared plus c. So we went ahead and integrate. Now we want to use our initial condition, which was -1, 0, and we plug this in. So when we use our initial condition, we end up with 1/2 e to the 2 times 0 equals 2 times -1 squared plus c. So you end up with 1/2 equaling 2 plus c. So 1.5 is going to be your c. So let's go ahead and write this now. So we end up with 1/2 e to the 2y equals 2x squared plus 1.5. And then we end up with e to the 2y after we multiply everything by 2, 4x squared plus 3. We want to go ahead and take the natural log of each side because we're trying to get rid of that e to solve for that y. So we end up with 2y equals ln, and you can put this in absolute values, 4x plus 3, and then go ahead and solve for y. So y is going to be 1/2 ln. These for the values of x that you pick anyway are going to end up being positive, so we could just say 4x squared plus 3. So that is the solution to that differential equation. Okay, for number 14, it says find a particular solution y equals f of x to the given differential equation with the initial condition f of 2 equals 0. So again, this is like number 13 up there. So let's take a look at what we have, and we're going to separate the variables out. So in this one, we'll end up with dy over 2y minus 1 equals dx over x squared when we separate out those variables. Now, solving this, we're going to end up with 1/2. We're going to integrate each side to solve it, and we're going to end up with, on this one, 1/2 ln of 2y minus 1, and you can go ahead and take the derivative of this and check it. So again, if you guess that, you have ln u. If you guess your u equals the 2y minus 1. So if you did it through that substitution method. But in any case, that's what you end up with there. On the other side, we're going to end up with negative x to the negative 1 plus rc. So now we're going to go ahead and solve this for y. Actually, let's go ahead and plug in the initial condition that we're given, f of 2 equals 0. So that means we're going to plug in the point 2 comma 0. So we plug this in and we'll get 1/2 ln of 2 times 3 minus the 1 and oops, this should be a 0, sorry. It's the point, we have the point 2 comma 0. So, and then we end up with, on this side, we're going to end up with equals negative 1/2, because it's going to be x is 2, so 2 to the negative 1 plus c. And then over here, this will be ln absolute value of negative 1, which will be ln 1, which is 0. So that whole thing goes to 0, so we end up with c equaling 1/2. So now let's finish this problem up, and we're going to say 1/2 ln of the absolute value of 2y minus 1 equals negative 1 over x plus our 1/2 constant. And solving this, we can multiply everything by 2 first, so we end up with ln absolute value 2y minus 1 equals negative 2 over x plus 1. Raise these e to those, raised to the ln 2y minus 1 absolute value. We're going to end up with 2y minus 1 equals e to the negative 2 over x plus 1. And we can clean this up and solve it, and we end up with y equals e to the negative 2 over x plus 1 over 2. So we added this 1 over to the other side, then divided by 2. So there we go. Let's move on to the next question, number 15. Number 15 says the graph of the function f consists of semicircle, 2 line segments as shown. Let g be the function given by the integral g of x equals the integral from 0 to x of f of t dt. All right, for this first one, we need to find f of 3. So for number 1, we have to find g of 3. So for g of 3, taking a look at what we have, this is an FTC problem. It's the integral from 0 to 3, since this is our g of x, 0 to 3, of f of t. So in this case, we've got f of t dt, which is going to be from 0 to 3 right there. We have to take this quarter of a circle, and we're going to add this. So we're taking the area here and the area there is basically what we're going to do. So this is a quarter of a circle, so this is 1/4 pi r squared, and in this case the radius is 2, so we'll say 2 squared, plus, now this is a triangle here, base is going to be 2, height is going to be negative 1, so we have 1/2 of, okay, sorry, so we're going from 0 to 3, I just noticed that 1/2, so we want the area right there. 1/2, this is a base of 1, and the height of -1. So this yields a value of pi minus 1/2. So sorry about that, what we did over here. Okay, now moving on to number 2. Number 2 says, for what values does it have a relative minimum? So for this, we are looking at for what values do we end up with a relative minimum. So we're going to look for the critical points here. And the critical points, and it's asked for the whole thing of x, does it have a, so we're going to take a look at everything. So the critical points on this one end up being -2, because there's a 0 right there, 2 and 4. So -2, 2, and 4, because these are my zeros of the derivative. So those are my critical points. So over here, let's put these on a number line real fast, and we could test to see what goes on. So we got -2, 2, and 4. So the region between -2 and 2, we have all positive. It's above, so the derivative is positive, it's above the axes. And the region between 2 and 4 is negative. And after 4, we end up with some positives. So we've got a relative maximum, positive slope, negative slope right here. So this is a relative maximum. So we've got a relative max at x equals 2 because g prime of x, which is our f of x, because we have to justify, changes from a positive slope to a negative slope. So whenever we have a change from a positive to a negative, that's going to yield a maximum. All right, looking at number 3. Number 3 says, for what values does it have a relative minimum? So we take a look at the same thing, and this time we're looking right there. It has a negative slope to a positive slope, so this occurs at x equals 4. And again, we could say because the slopes change from negative to positive. So that's where our relative minimum will occur. Okay, for number 4, for what values does it have an inflection point? So we got to take a look at all our possible inflection points here. And here what we want is we want f prime of x. In this case, we want that to be 0. So we are looking for horizontal tangents on this one, or kinks. So our possible inflection points, 0 is the obvious one, but then take a look. We are looking at a kink right there and a kink right there. So we have to test those points. So let's go ahead and these are the possible. So we need f prime of x equals 0. So the possible values of this, or undefined we should say, right? And that, which would be the kinks. So our possibles are at x equals 0 right here, horizontal tangent, the kink at 2, and the kink at 3. Now let's test these on a number line, and we're going to put 0, 2, and 3. We're going to test a region before 0, and these are all positively sloped. After we hit 0, and we're going to end up with negative slopes here, and then after 2 we end up with negative slopes, and then we get to 3, and then it goes to positive again. So we know inflection points are where the slope's going to change from positive to negative. So that's where it changes concavity. So concavity changes when f prime of x changes from positive to negative or negative to positive. And where does this occur? This occurs at x equals right here, 0, and at x equals 3. Those are the two spots where we end up changing. All right, so now let's take a look at number 5. Taking a look at number 5, I'm going to move this up a little bit so I've got a little bit more room. Number 5 says, write an equation for the tangent line to the graph of g at x equals 3. So at x equals 3, we need a slope there. So at x equals 3, 1, 2, 3 right here, our slope is -1. That's the value. So the slope value is -1. So we just simply look at the graph. Now, we need to know what our g of 3 value is. Okay, so we know that the slope is -1, so we need to take this a step further and find out what our g of 3 value is. So what we need to do is we need the integral from 0 to 3 of f of t dt, and we found that in the first problem. That's going to be pi minus 1/2. So that's our y1 value. This is y1. Remember, we have y minus y1 equals mx minus x1. Well, we know what the x1 is at 3. We need our y value. This is going to be pi minus 1/2. So we end up with, and we found the slope, so we end up with y minus pi minus 1/2 equals -1 x minus 3. So again, we needed the g of 3 value, which gave me this y1 that I was looking for, so that I can use that equation. All right, let's go ahead and move on to the next problem. Number 16. A particle moves along the x-axis so that its velocity v at time in that from 0 to 6 is given by that equation. Now for this problem, at time t equals 0, the particle, this is our initial condition here. At t equals 0, particles at x equals 1. So for this problem, we do need, we will eventually need our calculators for this problem. So let's take a look. For part A, we'll do it up here. Find the velocity and the acceleration. So we need v of 4 at time t equals 4. So we need v of 4. So this becomes 4 sine, and then when you put 4 in here, you're going to get 4 squared over 2 minus 2 times 4 plus 2. I'm just going to go ahead and tell you that this is going to end up being 2. Solve this, you'll end up with 3.637 units per second for our velocity. For part B, it says find the speed of the particle, or is the speed of the particle increasing or decreasing at time t equals 4? Well, at t equals 4, our velocity is positive and our acceleration is negative. So we need to find what the acceleration is over here. And I forgot to do that for part A, find the acceleration. So A prime, or A of t, is going to be v prime of t. So let's go ahead and put what A of t ends up over here. We will take our derivative, and this will be 4 cosine of this stuff right in here, which will be t squared over 2 minus 2t plus 2. Chain rule what the inside is, so that'll be times t minus 2. So we want this at t equals 4, so we end up with an acceleration of, go ahead and plug it in, use your calculators, -3.329 units per second squared. So that was for part A. All right, so now let's compare. This is what I was saying for part B. We have a velocity that's positive, and we've got an acceleration that's negative. Since velocity and acceleration are opposite signs, we know that it's slowing down. If they were the same sign, it would be speeding up, but since they are opposite signs, we know that it's going to be decreasing. So it is decreasing. Okay, for part C, it says find the time at which the particle first changes direction. So what we need here when it first changes direction is we are looking for v of t to be 0. So we set this equal to 0, and we got 4 sine of t squared over 2 minus 2t plus 2. The easiest way is to use your calculator and graph. And when you graph this, you will get some funky thing that looks like this. Comes down, goes back up, comes down, goes through here, then comes back up. So let's indicate what this is. This hits 0 at 2. This hits 0 over here at 4.5066. Remember, these are positive values over here. Positive. We'll talk about that in a sec. So where does this first change direction. So these are positive, positive, again, above the axes, and then below the axis. So we went from a positive value. It hit 0, but then it continued to be positive. So that means it's going, 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 stop, but then it continues to go. Here it's going, 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 stop, the velocity is 0. Now it's negative, so now it's moving in a backwards direction. So that's when it first changes direction at t equals 4.056, 4. Let's rewrite that correctly. This is going to be 4.5066. Again, think of it like this. It's going positive. It's positive above the axis. Velocity is positive. So the particle's moving, 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 stops. Then it continues to move. It's positive. Boom, it stops. But then it goes negative, so it starts going the other direction, so it changed direction. Describe the movement of the particle near time t equals 2. So what's happening here is that the velocity is slowing down, it's becoming a smaller value. So velocity slowing down, stops at 2, then continues and speeds up. Continues in the same direction, and it speeds up again because you can see that it starts to go higher right here on the graph. Okay, moving on to the next problem. For the calculator, these are all calculator problems, so let's take a look. A particle moving along the line has this velocity to find the total distance traveled from 0 to 3. So for the total distance traveled, we want to set this velocity equal to 0. Find out when it stood still, if it changed direction. So we want to take our positive directions, add them with our negative directions. So 0 equals this 3t squared minus 6t. We end up with 0 equals 3t times the t minus 2. So t equals 0 and 2. So at 0 and 2, these are where the velocity is 0. Let's test the point in between 0 and 2. We're going to get negative values. So if we put 1 into our equation, we get negative. Put 3 into our equation, we get positives, or go ahead and put like 2.5. So we're going to get positives. So it changes direction, changes at t equals 2. So we need to break our integral up. So we need the velocity, since these are negatives, we need the velocity from 0 to 2, and we need to take that absolute value, and then we have to add this to the integral. Remember, we integrate the velocity, that's going to give me my distance traveled. So then we have to add the integral from 2 to 3. So let's rewrite how this should be. This is going to be the absolute value of the integral from 0 to 2 of v of t dt plus, and now we know it's positive, I don't need to put the absolute values, from 2 to 3 of v of t dt. So finding each of these, put in our equations, we end up with t cubed minus 3t squared on the bounds from 0 to 2. I went ahead and integrated all in one step. And then on this one, t cubed minus 3t squared on the bounds from 2 to 3. Remember, here we need an absolute value. So this ends up being 4 plus 4. So our answer is 8. And it is none of these. It's not indicated on there. All right, for number 2, the table shows the values of some continuous functions and its first derivative. Evaluate the integral from 8 to 0 of f prime of x dx. So in this case, what we're looking at here for this one is we need to change this to be, first of all, negative from 0 to 8 of f prime of x, oops, this is an x, dx. So this integrating ends up being f of 8 minus f of 0. So let's take a look. What is f of 8? F of 8 is going to be right here, which is 7. F of 0 is right there, which is going to be, sorry, f of 0 is right there. So that's going to be 11. So this ends up being negative. So this will be negative 4, negative, so it'll be positive 4. So our answer is D for this one. All right, taking a look at number 3 here. For number 3, it says, let A be the integral from 0 to 1 of cosine x dx. We estimate A using L, R, and T approximations with n equals 100 subintervals. Which is true? Ooh, we're taking 100 subintervals on this. Now, do we end up with L left, basically the saying left, right, and trapezoid approximations with n equals 100. So what's happening here? So which of these ends up being bigger? Well, if we take a look at the cosine on the bounds from 0 to 1, we've got this type of thing. And right here is my triangles. If I do a left, notice I'm going to get a overestimate. So left is going to give me an over, which would mean if I did a right, let's take a look here, redraw it. If I did a right endpoint, I will get an under. So a right will yield an under. So a trapezoid, in this case, if we draw our trapezoids, so we've got this, and if we draw a trapezoid like that, see what's happening? We're going to get a T is going to be under. So the only logical conclusion here is right will always be not as good an estimate in this case as a trapezoid as the actual area as our left. So in this case, we end up with D. So the right will be the smallest, the left will be the largest, the area will be somewhere in between, and the trapezoid will actually be less than, we showed it right there, than the actual area. So this is what we end up with. All right, number 4, a particle moves along the x-axis. The position is given by this. What is the velocity of the particle? At the first instance, the particle is at the origin. So let's go ahead and find our velocity, v of t. We're going to take this derivative, and we're going to get negative sine square root of t minus 1. So let's rewrite that. Something happened with a little glitch in the software. So we said that we had v of t is going to be negative sine square root of t minus 1. Now we have to do the chain rule, 1/2 of t minus 1 to the negative 1/2. Now we need the first instant when the particle is at the origin, so we need x of t to be 0. So we can go ahead and use our calculator, solve for where this happens, and this happens at t equals 3.467. So we need v of 3.467, and again, just plug this in, and then you end up with negative 0.3183 units per second. Okay, so for number 5, it says the depth of water in a tide pool is given by this equation where t is a time in hours starting at midnight and h of t is measured in feet. What is the average depth of the water between noon and 3 p.m.? So we're looking here between noon and 3 p.m. So in this case, this is an average value, and it's an average value from noon to 3 p.m. So if you think about it, noon, then we've got 1 o'clock, that's 13. 2 o'clock would be 14, 3 o'clock would be 15. So we want from 12 to 15 on our average value. So we've got 1 over 15 minus 12, the integral from 12 to 15. Again, this is an average value of our equation that they gave us, negative cosine pi t over 12 plus 4, and this will be dt. So, continuing on here, just go ahead and you can do this on your calculators. We'll say on calculator since it is a calculator portion, and then we end up with 4.9, approximately that. So our answer is E, 4.900 feet. All right, let's move to our next one, number 6. So find the volume of the solid generally when the region bounded by the graphs x equals square root y minus 3 and the lines x equals 0 and y equals 6 are revolved about the y-axis. So we are looking to see when these are revolved about the y-axis. So let's go ahead and quickly take a look at what this graph looks like. So if you wanted to do this, we'd have x squared plus 3 equals our y if we solve this. So we've got this graph that looks like this, and it goes in that manner. And we're going to revolve this from, it goes from 0 to 6, from y equals 0, from x equals, bounded by x equals 0, and the line y equals 6. So y equals 6 is up here. And then we are going to revolve this about the y-axis. So this is our 6, and we're going this way. So we need our slices to be perpendicular, so we end up with dy's. So that means my equation needs to be in terms of y's. It's already set up to be like that. Perfect, we're good to go. And we want to go from here to there. We can find that point. That point's going to be 3, where it's going to cross. So we set this up, and we got the volume is equal to pi from 3 to 6, and we're going dy's. So this will be the square root of y minus 3 squared dy. And go ahead and use your calculators at this point, and you will get 4.5 pi as your answer. This will be cubic units. Okay, so now moving on to number 7. The population of the city increases continuously at a rate proportional at any time to the population at that time. The population doubles in 50 years. After 75 years, the ratio of the population P to the initial population P sub 0 is what? So since it doubles, we've got a ratio here. We've got, it's going to be twice our initial amount. Our e to the kt, we can say, and in this case it's 50 years. So we end up with ln 2 over 50 is what our r is. So in 75 years, we end up with p equals p sub naught e to the rt or kt, however you want to say it, and then in this case it'll be ln 2 over 50 times r 75. Now, since we want this ratio, we're looking for p over p sub naught and e to the ln 2 over 50 times our 75. So we can go ahead and solve this, and we end up with a final solution of p to p sub naught is going to be 2 root 2 over 1. So D is our answer to this one. Okay, number 8, the function f is continuous, and the integral 0 to 8 of f of u du equals 20 was the value of 1 to 3 x times f of x squared minus 1 dx. So let's take a look at what we got here. On this one, suppose we let u equal our x squared minus 1. And now du is going to be 2x dx, so du over 2x is what my dx is. Now the reason I'm doing that is because I want to substitute this f of u. Alright, so let's see what we end up with. Again, since it's in u's, I don't want to resubstitute. I need to find what u of 1 and u of 3 is from these bounds right there. So u of 1 is going to end up being 0. Again, I'm plugging it in here, 1 squared minus 1. U of 3 is going to be 3 squared minus 1, so that's going to be 8. So we end up with the integral from 0 to 8 as it said we should. So this integral from 1 to 3 of x times f of x squared minus 1 dx is going to be equal to this integral from 0 to 8 of x times f of u times du over 2 dx. With my whole substitutions, this will be 2x. Sorry, this is 2x, not dx. So these x's will reduce out, and I'll end up with 1/2 times the integral from 0 to 8 of f of u du. So we know that this whole integral, we know that this whole integral right here has a value of 20, because that's what I'm told. We want half of that, so we end up with 10 as our final answer. All right, what's the difference between EVT and IVT? Okay, so IVT and MVT. So I gave you a whole worksheet on that. So make sure you review all those. What the difference between, I'm going to add in IVT. Remember, IVT, if it's continuous from A to B, then M, you have to have a value M between f of A and f of B. Then there must be a C such that f of C equals that M. MVT means that the slope of the tangent will be equal to the secant. So in this case, what ends up happening is that you have, for MVT, remember we said you can connect them and then you're going to have tangents that are equal to that secant. So your instantaneous will equal your average, and I gave you the Ferrari example. Okay, and then for extreme value, that one basically we're going to have some sort of extreme value on a closed interval. We will have an absolute. All right, let's take a look at this one for number 10 now. Okay. Okay, so for the Garfield stomach, it contains 500 calories of food at time t equals 0. During the time interval from 0 to t, the Garfield consumes lasagna at a rate. So let's take a look and remember that this is a rate. And that's the rate that he consumes the food. He plays football with Odie and burns calories. So this is the in, this is burning, is going to be the out. So I got to admit that I got this question from a friend of mine. I'm not sure where he got it from, but it was a cute question, so I'm using it here. How many calories of lasagna has Garfield consumed during the time interval from 0 to 10? So the amount consumed is the in. So all we need to do is integrate from 0 to 10 L of t dt, and this one comes out to be 1039.864 calories consumed. Okay, now moving on to part B. It's pretty tight here. I didn't leave enough room for work, so we'll squeeze it in. Is the amount of calories in Garfield's stomach increasing or decreasing at time t equals 7? So what we need to do is we need to find L of 7 minus B of 7, so the in minus the out, and we need to subtract these rates. So we end up here with 149.1304 minus 145.9574. Often you'll see these on the AP test as shoppers entering a store or shoppers leaving the store or going into an amusement park as some leave an amusement park, or snow is falling at a rate but then melting at some other rate, or being shoveled out at a different rate. So it's the same type of question, they just always end up wording it differently. So this one ends up being 3.173 calories per minute, and so this is increasing. Okay. For part C, at time, what time is the amount of calories a maximum? And what is the maximum number of calories? Show the work that leads your answer. So over here we need to find when this rate is 0 to determine our maximum. So we need L of t minus B of t to be equal to 0. So you can put this in your calculator. What I suggest is put this whole equation, you could put like y1 equals this equation, y2 equals this equation, and then y3 just put y1 minus y2, and go ahead and graph that, see where it ends up being 0, and this will happen at time t equals 7.14926. Again, what I'm saying is y1, let's write it up here in a different color so you can see that. Put this as y1 in your calculator. Put this as y2 in your calculator. And then y3 will just be y1 minus y2, and you could just graph this. It'll be easier if you do it that way, so that way you have each equation separate if you need to refer to it. Okay, so now we did that. We got 7.14296. That's where it occurs. We're going to test this on a number line. So this is the 7.14926. We'll end up with positive values here, negative values after it. So the slope goes from positive to negative. Why is this a slope? Because again, it's a rate. We're taking a look at this rate. So it goes from positive to negative. So that tells me it's a maximum. And this is what led to my reasoning here. So to find now the actual what is the maximum number of calories, what we need to do is we need to take our initial, which is what he has in his stomach already, 500, plus the integral from 0 to 7.14926, and of this L of t that's going in minus the B of t that's coming out dt. So we can put all that in. That's what I'm saying. If you do that in your calculators, you can just say the integral and then put y1 minus y2, and then you'll end up with this equaling 663.41 calories as your max. So that is what the maximum amount is. Go ahead and check this though. You want to always test your endpoints. So test t equals 0 and also test t equals 10. At t equals 0, you'll get 500. At t equals 10, you'll get 549.441. So this is the absolute maximum at 7.14. Okay, for part D, what is the average rate? Let's go ahead and change colors here so we can kind of keep things separated. What is the average rate at which the amount of calories is changing on this interval? So the average, this is an average value question. So this is, as we said, an average value. So we want the average value from 3 to 7. So 1 over 7 minus 3 from 3 to 7, and we're going to have our L of t minus our B of t equation. And then you end up with 27.1643. So that's the answer for part D. That's our average. Now, at t equals 10, Garfield stops consuming lasagna but continues to play football. If k is the time when Garfield has burned off all the remaining calories, set up but do not solve an integral expression. So set up but do not solve the integral expressions. So we know at t equals 10 from part C, from what we solved here at t equals 10, there's our calories. So the integral from 0, or from 10 to k, of b of t, because he's still burning and not eating anymore, dt, is going to be this 549.441. Or you could have written this as 500 plus, so this is our answer, or you could have done it as 500 plus the integral from 0 to 10 of L of t plus, or I'm sorry, minus B of t dt minus the integral from 10 to k of B of t dt, set all this equal to 0. So you could have done it that way and gotten that equation as well. All right, number 11. We're almost there. On number 11, it says, the rate at which water is being pumped into a tank is given by the continuous increasing function R of t. The table of values of R of t for the time interval 0 to 20 units is shown below. So for this one, we have our table, and we are to use right-Riemann sums with 4 subintervals to approximate the value. This should right here be the integral from 0 to 20 of R of t dt. So the integral from 0 to 20 is just the sum of all the delta x times the heights. So if we take a look at this, and let's quickly sketch what's happening here. So if I quickly sketch this, I've got 4, I've got 9, here's my 0, I've got 17, and I've got 20. All right, at 4, the height is 28. At 0, the height is 25, and at 4, the height is 28. At 9, the height is 33, so a little bit higher. At 17, the height is 42, so even higher, and at 20 the height is 46. So you can see that it's increasing the whole time. So if I were to draw rectangles here, so if I were to just kind of like sketch this in just so you can kind of see, you can kind of curve it, doesn't matter how you curve it, and I were to draw rectangles out of these using right Riemann sums. So I'm going to draw that right rectangle. this right rectangle, this right rectangle, and that right rectangle. So first of all, you can tell that I'm going to get an over approximate here. So, but let's take a look at what we have. Is your approximation greater or less than the true value? So take a look at what we have. It's going to be greater since it's increasing. And we have right endpoints, we will get an overestimate from our actual value. So the integral from 0 to 20 of r of t dt should be less. So now, if I were to actually approximate this and solve it, we'd end up with the integral. Let's just do that now. The integral from 0 to 20 of r of t dt, and we're using our right endpoints. It's going to be sum of all our delta x's times the height, which in the first one is going to be a delta x of 4 and a height of, right there, 28. So 4 times 28. The second one will have a delta x. We go from 4 to 9. This will have a delta x of 5. And so this is 5. And a height of 33. Plus the next one, which ends up being a delta x of 8 and a height of 42. And our final one, 42, let's write 42 in there. And our final one, which has a delta x of 3 and a height of 46. All of this comes out to be 751 gallons. And we've already said that our estimate is going to be an overestimate. Okay, so moving on to the next part, it says a model for the rate at which water is given by this function. So this is the model for this rate. It's just being, they just tell us to use this. Where t is measured in gallons per minute, use the model to find the average rate. Again, this is an average rate of change from t equals 0 to 20. So this is an average rate of change. So we've got the integral from 0 to 20, and then over here we need to say 1 over 20 minus 0 of the integral from 0 to 20 of 25 e to the 0.3 t dt. Use your calculators, and doing this on your calculators, you're going to end up with 34.255 gallons per minute. Okay, now for part C, the tank contained 100 gallons of water at time t equals 0. Use the model given in part B to find the amount of water in the tank at 20 minutes. So in this case, we've got 100 as our initial amount plus our integral from 0 to 25, or 0 to 20, sorry, of 25 e to the 0.3 t dt, and this comes out to be 785.099 gallons. Okay, so I think on my calculator here I screwed up and put 0.03 instead of 0.3. So this answer, I believe, should come out to be 33,635.73. And on the previous part, for part B, that should have come out to be 1676.787 if you use 0.3 instead of 0.03. So sorry about that. Okay, so be careful putting in those values in your calculators. All right, let's move on to our very last problem here. Number 12. A ski resort uses a snow machine to control the snow level on a ski slope over a 24-hour period. The volume of snow added is modeled by this. The rate at which it melts, modeled by that. So it's pretty much the same Garfield question. We've got they're putting in snow, taking out snow. So let's take a look at what we end up with here. So for part A, compute the total volume of snow added in the first 6-hour period. So the volume is going to be the first 6-hour period of S of t. Remember, this is in, this is out. What's coming in, what's going out. So in this case, it's going to be the integral from 0 to 6, and this will be 24 minus t sine squared t over 14 dt, and all of this comes out to be 142.413 cubic yards added. Okay, so that's how much was added in that time period. That's how much accumulated. So for part B, it says determine the first time that the instantaneous rate of change of the volume of the snow is 0. So since we need rate of change to equal 0, what we're asked is we have to find this S of t, the amount added minus the amount taken out, the melted. We want to know when this is equal to 0, or you could think of it as when is S of t equal to m of t in this case. So you can graph this and see where it happens. So that's what I suggest, is to graph this equation and see where you do get a 0 out of it. And this will give you like another funky looking graph that kind of looks like that. And that 0 is going to end up being at 15.04. So that's when it occurs. Thus, at t equals 15.04, and this will be hours. Okay, so moving on to part C. Is the volume of snow increasing or decreasing at t equals 4? So at t equals 4, we need S of 4 minus m of 4. And we want to know what ends up happening here. We end up with 23.6822 minus the 11.8819, which gives us a positive value of 11.8003. So it is increasing. That's an 11 there, sorry. So it is increasing. Let's redraw that a little bit better. All right, so now you can also look at the graph, and since it's positive at that point, you could tell that it's increasing as well. So that's another way to do that problem. So part D now, it says, suppose the snow machine is turned off at t equals 6, set up but do not solve an integral, determine the time k at which the snow will be melted. You'll see these a lot on the AP test for part D. Set up but do not solve, and you'll have a k in there. So here at t equals 6, we have 50 plus our, so at t equals 6, we have our initial, which is 50, which is what they told us right there, our slope holds 50, and plus the integral from 0 to 6 of S of t minus our m of t dt minus our integral from, this is like doing it the second way I did for the other problem, m of t equals 0. Okay, and this ends up, or again, we could do it like I did the first way, since we already have this value of 194.4132 minus our integral from 0 to k of m of t. And we want this to equal 0. So either way, you could set it up and do it. All right, this was very long, and I understand that. I even made a couple mistakes because I'm getting tired here. So hopefully this will help go over some of these problems that students seem to struggle with. Good luck, study hard, and we'll see you next time.